Hello, everyone. So welcome to the second seminar in this series of informal seminars about our implementation of a process calculus in Isabelle Hall, the Thorne calculus. So we are still and will be there for some time in this framework for transition systems, label transition systems. And as I have explained already, this captures some common things that are common to different process calculi and different notions of behavioral equivalence for particular process calculi. And it's actually even more general, so at least a large part of it is not tied to process calculi at all, but just about label transition systems, which describe possible behavior of a system. So label transition system is, as we discussed last time, consists of a set, or here a type of states and a type of actions. States will correspond to processes when we go to process calculi. So therefore, I'm talking often about processes here and use the type variable p. But for now, this is just states, right? And the label transition system has a set of states and a set of actions or type thereof. And then it has a relation, a ternary relation between a source state, an action, and a target state, which I here describe in a bit of a different order. So here you have this canonical order, right? So it's a relation, it's a function to bool. And here the action comes first, and then because of currying, you can map an action to just a binary relation on P. And it's this P relation type synonym that's used here. So, and as I said last time already, we have to first describe the more general notion of what I call a simulation system, because we will go to describing what bisimilarity is, the notion of equivalence, and we have the notion of simulation, bisimulation. And the point is that normally we would say, okay, some step in the label transition system can be simulated by another step from a corresponding state. But in general, the simulating system might be different from the kind of system from which we start. And this will be in particular the case when we go to this notion of what I call mixed simulation, mixed bisimilarity, which is an alternative definition for weak bisimilarity and the corresponding simulation bisimulation notions. So in weak bisimilarity, we ignore certain internal actions, and we do so elegantly by deriving a new transition system from the original one, where one step can make certain internal steps in addition to the actual step. And the idea of this simulation is then if you do such a weak step with possible internal transitions added, then we can simulate it by a weak step. But actually, we can also just prove that if we have an original step, it can be simulated by a weak step. And that leads to the same notions, and it's much similar to proof. But then you have the distinction between the original transition, which is the actual one, and the simulating transition, which is the weak one. And therefore, we first describe here the setting where these relations can differ, and later we will have the transition system, which is just a simulation system where both are the same, and then we will get some additional properties. So what I didn't describe so far is this locale construct. So locales in Isabelle are something like type classes on steroids. So if you go back to Haskell type classes as they originally were, so no higher kinded types in there, and no multi-parameter type classes and all these things, just basically classes of types of kind star. This is also what Isabelle has. It has a class construct. But in addition, Isabelle allows us to specify properties that the operations have to fulfill, which makes very much sense for a theorem prover, and which is also in line with how we think about type classes, hopefully. I mean, there was always this lot of fuss with the monad class and the monad tutorials that you have these axioms, these properties. But actually, this is not specific to the monad class, as it was often suggested. It's specific to any class. or virtually any class. For example, the order class also has associated axioms like that, this thing that's described as a total order. And in Haskell, you cannot specify these, only informally, but in Isabelle, you can. And then whenever you instantiate a class, you have to prove that these properties hold. And this is a really neat thing. And this is for type classes in Isabelle, but locales are more general. So locales can be, in a sense, multi-parameter. You see here the two type variables. And for locales, you have these so-called interpretations, which correspond to the instantiations or instances of the type classes. And there can be several interpretations for the same tuple of types, which is often a good thing. For example, if you think of natural numbers and you want to treat them as a monoid, so I mean, there are several possibilities. So the operation can be the addition or the multiplication or the minimum or the maximum. And in Haskell, you have to always decide for one, and if you want to treat several, then you play tricks with new types, and it becomes a bit ugly. I mean, type classes have the advantage that you get this automatic resolution, that it finds the instances automatically. But with locales, you are more flexible, and it captures the principle that there, in general, is no single sensible instantiation of some algebraic structure, in a sense, but that there can be several ones. And that's, of course, very important here, because for a single type of processes and single type of actions, in our case, for our particular calculus, which has a certain type of actions, certain type of processes, we want to have several instances or interpretations, to use the terminology of locales. And therefore, we cannot use type classes here, but we use locales. And we say, okay, a simulation system is characterized by an original transition and a simulating transition. And we could add some axioms also, like with type classes. It's just that here we have the interesting corner case that we don't have any axioms. So any relations are fine. So they don't have to even be related with each other, right? So they can be any random relations that have these types or this type, and it will work out, and we will see this by all proofs going through, so all proofs being accepted. Okay, and now what we actually want to get to is this notion of bisimilarity. Two processes are bisimilar if they basically have the same behavior, or in the general context of state systems, two states are bisimilar if you can start on either one of them and then execute actions to go to new states, and the behavior is basically the same. It's a very strong notion of behavioral equivalence. It's not just concerned about traces in the sense that you look what sequences of actions you can execute, and if these are the same for both processes, then they are equivalent. It's stronger than that. It also looks at where you get non-determinism, right? So it's a difference whether you execute some step, some action A, and then you can decide if to execute B or C afterwards. Or alternatively, if you have decided right up front whether you want to execute AB or AC, this is something that some path concerning equivalence wouldn't distinguish, but bisimilarity does distinguish it. And if I remember correctly, you won't get compositionality, certain forms of compositionality, if you would not do this. So what we want to do is, if we want to have, if you have a big system, you want to be able to just look at parts of it and then see, and then be able to prove that the replace some small part of the system or some small part of the process by some process that's bisimilar to the original one, then the whole system stays basically the same in the sense that what we get is bisimilar to what we had before. So that's very important, of course, so that you can reason about modules and then deduce then behavioral equivalence for the whole system. So we will now look at bisimilarity, and I first want to explain a bit the whole picture because of the following. If we start here in the code, then it starts with some things called unilateral and bilateral progression. And that's already a very, very general concept. And it's only there because we will have later simulation and bisimulation, but for the sake of easier proving, also simulation and bisimulation up to some function. And so these are already 4 different constructs. And in particular, we have these ordinary notions and these up to notions. And to capture them both, I introduced this progression notion, which also comes from the literature on process calculi, and which generalizes both of them, but right immediately it's not really understandable perhaps why we want to have it. And therefore, let me just switch to some diagrams. And so here we have a diagram which basically captures the idea of what the simulation and the bisimulation relation is. So K is a simulation relation if the following holds. Whenever we have processes P and Q that are related by K, so the arrow just depicts in what direction the relation K goes, so to say. So P is related with Q, not the other way around. And whenever we have that, and we can make a step from P to some P prime with some certain action alpha, then it must be possible to go from Q to some Q prime with the same action alpha, such that P prime and Q prime are again in this relation, which of course results in the fact that if now I can go from P prime with some action alpha, maybe some different action alpha prime, to some P double prime, then I can again simulate this with a transition from Q prime, and then again I'm in the relation, and so on and so forth. So K is a simulation relation if in the end this P can be simulated by Q, or the transitions from P can be simulated by transition from Q, and this can go on forever. So, and it's a bisimulation relation if this also works for the converse of K. So if P, so we had if P is in relation to Q, and we can do a step here, we must be able to simulate it by step here and get into something that's in this relation again. But with bisimulation, we have the additional condition that if Q is in relation with P, yes, if Q is in relation with P, so if P is in converse relation with Q, and we can go from Q, no, so sorry, I was wrong, not get confused. It's always P in relation with Q, of course. If P is in relation with Q, and Q can make a step to Q prime, then we can simulate this here, and P prime is in relation with Q prime again. So this step can be simulated by that, and this step can be simulated by that, or by one on this side. So it's bisimulation. And of course, we have to have now this interesting thing that if K is a bisimulation relation, then we can simulate steps here by steps here and steps here by steps here, get in the relation K again, and then we can continue with this because these are again in relation K, and then we can play the same game. So in particular, it must be possible, for example, if we have a transition from Q to Q prime, we can simulate it by a transition from P to P prime, get in this relation, and then also relation from this P prime to some P double prime as then to be able to be simulated by a transition here. So it can, so to say, change sides during this process. That's bisimulation. And now bisimilarity is just the largest bisimulation relation. You can prove that there's always a unique, always one largest bisimulation relation. This is bisimilarity. And alternatively, you can define bisimilarity by co-inductive definition, because this gives you a largest relation that fulfills certain properties. You can just say bisimilarity is the largest relation for which you have the property. If you make a step here, you can make a step here and get in this relation again, and vice versa. So, and this bisimilarity, this is a rather strong notion of behavioral equivalent. So sloppily speaking, it's hopefully clear that it means something like, okay, everything you can do here, you can do there, and you can swap the roles at every step. So basically these states are not indistinguishable, right? And it would, for example, I think be possible to just collapse them and treat them as the same. And this is our fundamental notion for our proofs later of properties of programs. So we want to prove things like this more refined program is equivalent to the program that with which we started, or this program is equivalent to specification, because the process calculus is also good to phrase specifications. But because bisimilarity is well understood, well behaved, it's a very good thing to use this as our key notion for specifying properties of processes. Because if you have several good properties, several lemmas that say, okay, processes of this structure are always bisimilar to processes of that structure, which we have, and you can often just compose these lemmas to get more stronger results about correctness of your programs. However, at some point you have to go down to the basic bisimilarities, the basic bisimilarity in lemmas. This is bisimilar to that. Things like, for example, commutativity of parallel composition. So if you have a process that composes P and Q in parallel, and you have another one that composes Q and P in parallel, these two are bisimilar. But not to prove that, you must go directly down to the label transition system and refer to this definition. And then sometimes you get this interesting phenomenon, which makes it hard to do these proofs. You say, okay, when I go with P to P prime, what possibilities I have? And sometimes you have the situation that it looks like you could use a relatively simple and small relation K, for which you prove that this is a simulation relation or bisimulation relation. And then, for example, in the case of parallel composition, you say, okay, my relation K relates P parallel Q and Q parallel P. And if K is a bisimulation, then this P parallel Q and Q parallel P are bisimilar, because every bisimulation is included in bisimilarity, since bisimilarity is the largest bisimulation. However, what we ideally would want to do, for example, in this parallel case, right? So we write it here quickly. That is P parallel Q should be bisimilar to Q parallel P. We have to define a relation K that includes this pair, P parallel Q and Q parallel P. And ideally, we would maybe like to define K such that it only includes such pairs, and then prove whenever we start with a P parallel Q and make a step, we get into some P prime parallel Q prime, for example. So, and we can simulate it with a step here from the Q parallel P, which is now this Q here, and get into Q prime parallel P prime, so that we simply are in this relation K again. So the structure of these terms, these programs, doesn't really change when we make a step. So we can define our relation K such that only such pairs are included. However, this is often not possible. Often, for example, we don't get quite into such a pair here, but into something that it's only in this relation K up to something, up to bisimilarity. We get to processes that are not really in this relation K, but which have processes bisimilar to them, which are in K. Or we get into processes that are not in this relation K, but because they have accumulated some sort of context, that some additional stuff that has to be executed. So we will see examples of this later. And then we have this annoying thing that our relation K is too simple. We have to account for these changes that can occur to the structure of these proofs while we make steps. And then we have to blow up our relation K and include all these slightly changed notions of how processes can be related with each other. So the general principle is we are only interested in processes PQ in this diagram, which are in some simple relation. But as we make steps, they are not in this simple relation again, these P primes and Q primes and so on, but into something that's almost this K, but there are some changes. And then we have to include all these changes also into our relation K. And we get a quite complicated relation K, and we have to deal with these slight modifications to the original K we had in mind, although these modifications or these extensions can be handled mechanically, and they are handled the same in every proof. And we have a lot of boilerplates. Every proof has to deal with the fact that's not quite in this original relation, but it's in some K up to bisimilarity or up to these contexts. And our goal is to handle these technicalities once and for all, so that someone who wants to do bisimilarity proofs can get away with showing things only for the simple K, and it is allowed that on this side, the processes are not directly in relation K, but in something modified. And this is what we have here. So this is simulation and bisimulation relations up to some function f. And this K is a simulation up to f, which is a function on relations, if we have the following situation. Whenever P is in relation K with Q, and we can make a step with P, then we must be able to make a step with Q, and these P prime and Q prime, they are not now forced to be in relation K, but in relation F of K. And this F can then, for example, extend or somehow otherwise modify this K. And then it's often possible that we can really use a simple relation K. If we make steps, we get into something slightly more complicated, but this is what the F is accounting for. The F includes those pairs that are not quite in the relation K, but only almost, so to say. And in fact, there are many of these functions F which permit us to just prove this here, simulation up to this F, and still deduce that this K is included in the bisimilarity relation, so that we can conclude P and Q are bisimilar. And this, of course, doesn't hold for all functions F, but there are certain functions F for which you can definitely say that they allow this conclusion, and these are called respectful, and we will see this soon. So, and in our general framework, we prove once and for all, if F has the property of being respectful, and there's a proof that, so to say, this diagram not quite commutes, but that what I just described, that this simulation up to F is possible, then we can conclude that P and Q are bisimilar, or more generally, that K is included in bisimilarity, although we don't have the K here, but something modified. Are there any questions up to this point? Okay, let me then go a bit further. So
sorry, I had a question, but I was being interrogated by my son shooting at me.
Okay. Yeah. Apparently you're not yet shot. I'm happy about that.
No. I was shot, but not with a real bullet. So,
okay.
Yeah. So let's see. I was wondering, is this F kind of fixed when you define it, or is it that you only describe part of its properties and it's open-ended otherwise?
The F, so for every particular proof up to F, you fix an F. And so you fix an F and prove that for all your P's and Q's, like this parallel composition, for example, it is a bisimulation up to this particular F. But for proving another property, you can choose a different f. So bisimilation up to a concrete f can be proved for a particular bisimilarity lemma that you want to prove, and then you can conclude that your P and Q are bisimilar. But for the next proof, you can choose a different f. I don't know if this answers your question or.
Well, I was just asking about the norm in the proofs, and I think that you answered my question. But then, is there any point in wanting not to fix f? Would it not be more general if I say that for example, for every bijection from that set to the other set, then I prove simulation and bisimilation up to every such f. Is that just not more general? And is there any reason why not to want that?
So that you want to prove that certain processes, or you want to prove that a certain relation K is a bisimilation up to any f?
That has a certain property, for example.
Yes. Well, but this would make your job harder. So the idea is that you actually, in the end, are not interested in this up to stuff. You want to prove that K is included in bisimilarity. And to make your job simpler for proving that, you are allowed to pick a particular f that has this respectfulness property and just prove it for this particular f. And this already allows you to conclude that K is included in bisimilarity. So you pick your f such that it's convenient to prove your particular bisimilarity statement. That's the idea.
Okay. Okay, I got it. Thank you.
And as we will see later, so there are some basic f's that have this respectfulness properties, but then there are also certain functions that can create new such f's, new such functions on relations from existing ones, and which preserve respectfulness. And so you can build your up to methods, you can build your f's by some small algebra of such operations. And then you can often really construct yourself a customized f, which is exactly the right or the best f for your particular proof. You define the f in such a way that you can precisely avoid the boilerplate and concentrate really only on the essence of your statement. So that's the idea. So what we prove in the general framework is that for every respectful f, we have this property that from proving this, we can conclude that K is in the bisimilarity relations. So this is a strong statement. And this allows us later to pick one fixed f, prove only things for this tweaked f, and then conclude K is in bisimilarity, P and Q are bisimilar. More questions? Okay, so let's go to progression then. This is this general notion that I quickly showed before in the code, or where I mentioned that we still start with this. So originally in our old calculus implementation, we only had simulation and bisimilation, and it was very simple. And now we want to have also this, and of course this is very similar to that, but we have this f here now. And actually, of course, we could see this as a special case of that, right? We just pick f to be the identity. So we could start with the notion of simulation up to f and bisimilation up to f, and then just treat this as a special case. However, in our proofs, that from bisimilation up to f, we can conclude that things are bisimilar. In this proof, we will not always have this scheme, but again, something slightly different. And what we do in the end is we generalize this whole scheme here and say, okay, in general, we define the notion of progression, which just allows this on the right to be any given relation, right? So we have two relations K and L, and we say the relation K progresses to the relation L if and only if a step here where we have a P in relation K with Q can be simulated here such that the resulting processes are in relation L. And obviously, one moment, we can define this and also this as special cases of that. So we then can define a relation K as a simulation up to F if K progresses to F of K. And it's a simulation if K progresses to itself. So that's the idea. And now we can see how we encode this in Isabelle. And now there's some neat thing that we can do. We could break this down to logic and just say, just describe it how I described it here all the time. For all P and Q that are in relation K, and all P prime where P can, and alpha, all alpha where P alpha P prime is a step in the transition system, there exists a Q prime such that Q goes with this alpha to Q prime, and this P prime is in relation L with Q prime. However, whenever we work with relations and logical statements about them, we can also use operations on the relations. Operations like relation composition, or also relation inclusion, which would be set inclusion if you represented a relation as sets of pairs, and which you can also define for these Boolean functions in an analogous way. And then we can make things quite neat. So the point was here in the definition, we said, okay, whenever we have a P and Q that are in a relation K, and we have an alpha and a P prime such that we can make this transition. So from the P we go here, and then we must be able to go here and, so to say, here with the relation L. However, if we look at the converses of K and L, the ones that go this way, from bottom to top, then we could say, okay, if Q is in the converse of K with P, and P is in relation to P prime, of course, we could express this by a composition. So if Q is in relation with P prime via the composition of the converse of K and this transition fixed to alpha, then Q must also be in relation with P prime via the composition of this transition step and the converse of L. So we have already introduced this composition here. So we have eliminated this with the there exists a Q prime, because this is inherent in the definition of relation composition, that there must exist this intermediate thing. But now we said, okay, if Q is in relation with P prime via this route, then it must also be in relation with P prime via this route. And this just is the same as saying, okay, this composition, converse K and transition, is included, is a subrelation of this composition, transition and then converse of L. And this is how we specify it in the code. And this makes it very nice to reason with this later, because we can do it in a kind of point-free style. Often we do not have to refer to these P's and P primes and so on and so forth, but we can do equational reasoning or reasoning with inequalities, and we get very, very clean proofs. So how does it look? Let me save here. Well, it looks like that here. So we first define the unilateral progression, which is the one that I have described so far. This is a relation between relations, right? So again, we want to say K progresses to L if this thingy with the diagram holds. So K is a relation, L is a relation on processes or states, and progression is now a relation between K and L, or between relations. So it's a relation between relations, and we use this harpoon arrow because it's unilateral, so we only have something on one side, and here we have it on both sides. This is this arrow with a small line. This will then be bilateral progression. This is like with simulation by simulation. So how is this unilateral progression defined? So this is a definition, and we say K progresses to L if and only if this holds. So last time I've said that in definitions we write equals here, but if we have Boolean functions, then we can also write this if and only if, because this is just a abbreviation in Isabelle terms of the equality for the type restricted case that both sides are Booleans. So this gives us a nice mathematical notation, but it's a definition. This is defined to be that on the right-hand side. So K progresses to L if for any particular action alpha that we fix, well, this composition is included in that composition. So the smaller or equal is here, of course, has nothing to do with numbers. It is a operation from a type class, something like OR, so to say. And this is general for lattices. And so for sets, it would be set inclusion. So for relations defined as sets, it would be this relation inclusion. But if we define relations as these Boolean functions, it is also the relation inclusion, because the lattice structure of functions to the bools are defined this way. So the bools have a lattice structure, and then functions to bools also have a lattice structure where things are defined pointwise. So for any particular alpha, if we go up on the left in the diagram, so the converse of K, so remember this is just converse, right? This is not a double converse. Also, this is just this notation if you have relations represented as Boolean functions. So if you go converse K, so on the left side from bottom to top, and then this is composition, remember? And then if we make a step with this original transition with alpha, then this composition is included in first making the step on the bottom and then going up on the right-hand side with the relation L. Of course, here we distinguish between the original transition and the simulating transition. So in the diagram, I always wrote the arrows, but actually it would be more precise to say that this is the original transition. I won't write it here, but I hope it's clear. So this is the original transition, this is the simulating transition. So that's unilateral progression. And now bilateral progression is like bisimulation is to simulation. It just says that we can also play this game with the roles of P and Q swapped. So K progresses bilaterally to K if K progresses unilaterally to K. So we have a bilateral progression from K to L. If we have a unilateral progression from K to L, and we also have a unilateral progression from the converse of K to the converse of L. So in this diagram, if we look at the converse of L, well, this relates Q with P instead of P with Q, and likewise here for the L. So it's basically swapping the bottom line and the top line, right? And this gives us this situation that we look at transitions from Q to Q prime and seek to simulate them in a way by transitions from P to P prime. So we say if we can make a step from here to here, and P is in K with Q, which means Q is in converse K with P, then we can make a simulating step here, and this P prime is in relation L with Q prime. Please note that the relation with which we start, which we already have, the transition, sorry, this is always the original transition system that we consider, and the one that simulates it is always the simulating transition system. So if we look at this forward simulation that we had all the time, where we say, okay, we have a step here, and then we must have a step here, then this is a step in the original transition. This is one in the simulating transition system. But if we start with the Q side and then simulate with the P side, then this must be in the original transition, and this must be in the simulating transition. So it's not that the first argument of K is original and the second argument of K is simulating. That's not the case, but it's always that the one that we start with, be it this or that, is original, and the one that must simulate it, of course, is in the simulating transition. So, any questions to that?
So just to clarify, the composition of relations is, let's say, backwards than usual mathematics.
Forward. The function composition is backwards, but the relation composition is forward. So this step, the step in this relation is made first, and the step in this relation is made second. So first converse K, then transition, and this must be included in first transition, then converse L, and this corresponds to what we had in the diagram. First, so from the Q, first converse K, and then transition, which is the same as being able to go from P to Q with K and have this transition, and then first transition, and then converse L. So if you make a transition here, this P prime is in relation with this Q prime. So that's maybe a bit confusing because with function composition, it's exactly in the opposite order. So if you convert a function to a relation, then you have to be careful to switch sides. More questions? Okay, then let's go to simulation. So simulation and also bisimulation. So the notions of simulation and bisimulation are now pretty simple now that we have this unilateral progression thing. So as I said before, we consider this diagram, and this is like this diagram just with L being the same as K. And so simulation, this relation is a simulation if it progresses to itself, right? And it's a bisimulation if you have this bilateral progression to itself. And here we would just have from K to F of K, but this will come later in the code. But I wanted to explain it here in order to motivate this general notion of progression. So, yes, so that's what it says. The simulation here, this is a predicate on relations. So here we had a binary relation on relations. This is what's the unary relation on relations, so a predicate on them. And so K is a simulation if and only if K progresses to itself. And likewise for the bisimulation, K is a bisimulation if K bilaterally progresses to itself. So that's very simple. Maybe some notes again about Isabelle stuff that we have here in addition. So here we have again some alternative syntax specification. So every entity that we define always has a name, but we can add operator notation in addition. And we say we have these infix operators, which gives us the infix notations and also the possibility to put parentheses around these things, like in Haskell, and then use them prefix also, or just on their own. And for simulation, I have done something nice here. I said, okay, this is some mixfix notation, but it's a mixfix notation without any place for any parameters or arguments. So the simulation function as a whole can be also written sim. So this is like an alternative identifier or an abbreviation for it also. This is because I want to write them in this short notation. And later we will have a notation for simulation by simulation up to, where we have then some special place for the F. It's not really written as a function argument. So, and this is to make it in line with that. But we could now write simulation, and equivalently we could write sim, and it would be the same. And maybe about this if and only if attribute here. So we saw already in this foundation theory, this simp. And I said if we mark these things, these equations with simp, then they will be automatically considered as rewrite rules by the simplifier that is invoked by several of these automated proof methods. And if and only if is a bit stronger, it works for equalities that are logical equivalences. So we have pools on both sides. And this if and only if includes the simp, so the simplifier will consider these things as rewrite rules and automatically do corresponding replacements. But in addition, certain reasoners that do logical reasoning will also consider these rules. So even if they don't use rewriting like the simplifier. So it's just to make it considered as often as possible by default, which is not always a good thing. as I said before, sometimes you don't want that, but we have this policy that we basically always add it, except for these situations where it really would cause trouble in our formalization. Because then we don't have to explicitly mention, use the definition of bisimulation or use the definition of unilateral progression, because it would be a bit boring. Okay, questions to this point? Well, then let's go to bisimilarity. And I said bisimilarity is the largest bisimulation relation. There's always a single largest one. And we could specify it like this. That's the largest one. And then we would have to prove that there can be only one. But we can also go a different route. We just define it co-inductively. And co-inductively defined relations are largest relations that fulfill certain properties. So it boils down to the same thing. And we can know this by knowing what co-inductive means. However, we can also prove that, and this is what we will do, or have done, of course. So let's define this notion of bisimilarity, the central notion of behavioral equivalence. So bisimilarity is just a relation, and it has this infix notation with this tilde. And so we have this co-inductive definition, and now we can have several clauses like with an inductive definition, but here we only have one. And now we have bisimilarity colon here. So this is something different from this. We just use the same name because we only have one clause. This names this clause or this alternative. This is like a bit, if you would think of this definition being a GADT of proof terms, which you could have kind of in Coq or even in Haskell in a way, then this would be, so to say, the data constructor name, perhaps. Well, yeah, in a sense. What it actually is, it names this fact. So this is, in a sense, all this thing below this bisimilarity colon is, in a sense, a logical statement. We will look at the details soon. And bisimilarity is a name of it. So Isabelle has the notion of facts. A fact is a proposition that Isabelle knows to be true. For example, a lemma or theorem is a fact because it's proved. But also this is a fact because we define the bisimilarity relation using these clauses, and these clauses correspond then to logical statements that are true for the bisimilarity. It's a bit similar to these definitions that we had here, right? The equalities, and also these logical equivalences here. We define our constructs here, our functions, using these statements, and then these become facts. These are true. This is where we start. And this will also become a fact, and this is the name of the fact, and this is why it's standing here, so that we can later refer to it. So, but what does this fact say? So we could write this fact, we could write this clause as a implication statement saying this thing and this thing implies this thing above here. However, Isabelle has this outer syntax, which is outside of expressions, where we have these keywords if and and this boils down to the same thing. So we have these three propositions here, this, and that, and these keywords if and all together denotes, again, a logical statement. And so I can show it to you, actually. After you have this co-inductive definition, this bisimilarity here names the logical statement. So it's kind of a theorem or a fact, and we can query it. We can say theorem bisimilarity. And then you see it down here, right? So we have this is covering, it's here, right? This implies that, this implies that. Don't be confused by the question marks. These basically denote that this P and Q there are universally quantified things. So you see it's basically the same thing as we have here. It's just that this is somehow nicer. So we will often use this outer syntax, which corresponds to mathematical papers where you don't write everything as big logical statements, but you also have some prose inside. If we have this and we have that, then we conclude blah, blah, blah. And this resembles that. So, but what does it say? Okay, we say P is bisimilar to Q if we have the following. For all actions and all p prime that we can go to. If we can go from p to p prime, this is the top side in our diagrams, then there exists a q prime such that we can get from q to q prime, and the p prime and the q prime are again bisimilar. So this is broken down to these logical statements, because here we cannot deal with compositions because we have to have this separately, because the bisimilarity is what we define here co-inductively. And this is the opposite direction. So for any alpha and q prime, if you can go with alpha with the original transition to q prime, then there exists a p prime on the top right now, such that we can go with a simulating transition system to p prime with this alpha, and the resulting ones are related. And since this is a co-inductive relation, this will generate the largest such relation that fulfills these properties. Does this make sense?
Perhaps you can explain the difference between the meta level universal quantifier and implication and the whole specific for all and implies.
This is what I just wanted to do after the question.
Sorry.
So, as I said, Isabelle is a metalogical system. It has this Isabelle pure logic, which is quite simple logic. It's a higher order predicate logic, so in that sense it's not simple. But for example, it doesn't have existential quantification, it doesn't have disjunction, and so now I can't get the word. Not intuitive logic, intuitionistic logic. Oh my. It's an intuitionistic logic, but Hall is built on it as an object logic, and that's a classical logic actually. So, and I mentioned this already, this pure logic is just used to define object logics as kinds of embedded domain-specific languages. So you can use this pure logic to describe the rules of your object logic. For this, you need universal quantification, but no existential quantification, for example. Right? So these logical rules with the bars and so on, they have some implicit universal quantification of the free variables, and the bar is some kind of implication, but you don't need the or the exists. And so now this is the universal quantification of Isabelle pure, of this meta logic. And this is the implication of also pure, the meta logic, but the meta logic doesn't have an existential quantification. So this is existential quantification of the object logic Hall that we are working in here. And now this is the conjunction also of Hall, not of the meta logic, because this conjunction here comes under the existential quantifier, and under the existential quantifier of Hall, the object logic, there can be only object logic stuff, no meta logic stuff anymore. This is because Hall introduces the Boole type, and this exists and for all and all the other logical connectives of Hall, they work with the Boole type, but this is a Hall construct, and these metalogical connectives, they work with some kind prop for propositions, or truth of propositions, also or proofs of propositions, like similar to Coq. And so this double arrow here, maybe I can even show it. Let me check. The double arrow has type prop to prop to prop, right? But for example, the Hall conjunction, has type bool to bool to bool. And also I could show that it exists it's a bit harder because it's a binder, but it also works with bool. That's the bottom line. And therefore we have to mix them. Of course, we could do all in the object logic. We could use the connective, which is a long single arrow. This is the Hall implication, which has the bools, and we could also use the for all, the ordinary for all that you know, which is the universal quantification of Hall, and phrases all in this with this Hall operators. This would be, in a sense, the cleanest way, you could argue. However, many of the proof tools are more general than just working for Hall, and they work with this meta-logical connectives, and then we would always have to explicitly turn, or often have to explicitly turn the Hall ones into the meta-logical ones, and it would make the proofs hard to read. And therefore, the typical style is that you tend to use the meta-logical connectives when it's possible. And you might think that's a bit annoying, and I agree, it somehow is. However, you can understand it in a different way, and then it's maybe not so annoying. As I said, these meta-logical connectives, they are used to specify the rules of your object logics. And if you think of this double arrow from the meta-logic Isabelle Pure as being a bar in some logical rule, and this is just this implicit quantification of your free variables or so, then it might make more sense, because then you can read this not as a single logical statement, but just as a kind of rule where this is on top of the bar and this is below the bar, and then maybe it's more convenient to understand. Maybe in this example, it's not so convenient because this whole thing is also is about pure implication. So we saw this here, right? You have this implication, the arrow here and the arrow here, but then in the parentheses you have these arrows. So it's now as kind of a nested rule, which is a bit like if you have in, I think it's the same like if you have in natural deduction these dots and the things in the brackets. Yeah, but if you wish to think of it as rules, then you at least have some sort of justification for this mix of meta logic and object logic. So, and if you don't want to care about this, just ignore whether it's a double arrow or a single arrow. It's always implication, and same for this guy here and the ordinary for all quantifiers. It's always universal quantification. More questions? Okay. We don't have so much time. I'm not sure whether I want to go into details here with these proofs. At least I want to give you an overview now, and next time either we go to the details or we look at the details of other proofs, because this would just boil down to describing more Isabelle specific stuff. So here we have a few lemmas about this bisimilarity. So first we have the lemma, the bisimilarity is symmetric. And now you have here this assumes and shows. And this is similar to this if and and. So this is, again, some outer syntax, which allows you to phrase this in a kind more prose-like style, which we are using here throughout our formalization. But in the end, you get some logical statement. You can see it by doing a query. So if you look at this bisimilarity symmetry rule, then we have a meta-logical implication. So these outer syntax guys, they give you meta-logical constructs because they are also not tied to Hall. They are a general Isabelle concept. So this is the lemma statement that you effectively get if you write assumes this, shows that. This specifies what this lemma is saying. And this is the proof that I only want to skim over today. So it says, using the assumptions, which is where there's only one, namely this, I can prove this by invoking co-induction, the co-induction proof using this rule basically, and invoking some automated reasoners, and this already works. So it's simple enough that Isabelle can figure out how to prove it with very little help. Essentially, you say, okay, just do co-induction, so it applies the co-induction rule to simplify the goal, and then you have to invoke some automated reasoners in order to solve relatively trivial statements. We can, if you want, we can go through the details next time, and then I can also show you what the intermediate goals that this co-induction thing creates are, and so on. So bisimilarity is symmetric, and this comes from this inherent symmetry in the definition. So basically say, okay, if you make a step, so here you have to prove if you make a step, then you can make a step on the other side and get into something bisimilar. And it also holds the other way around, because you have both sides. So you can also make this step first and then make this step, get into this situation. And since this is again required to be symmetric, then you can complete your co-inductive proof. That's the vague description. So, and then we have bisimilarity symmetry. It's basically the same as here. It just uses a predicate simp that's defined as the standard library. Simp applied to some relation is true if and only if this relation is a symmetry relation. The P comes from the word predicate. Sim without the P would be the same thing for this sets of pairs representation. Sim P is the thing for the predicate, the Boolean function representation of relations. So sometimes this rule, this more lower level rule thingy is good, where you have the implication. Yeah, you see it here also. This is good in proofs, because these rules, so to say, that use the metalogical implication, these can be often applied then directly by provers. While this is more high level, it says directly this is a symmetric relation, but in order to use it in proofs, you would have to first employ the definition of this sim P predicate in order to make use of it. Therefore, we have both, and then the same for the bisimilarity. But no, not quite the same. No, it's something else actually. This, I was talking nonsense. Sorry, this is about bisimilarity. It's symmetric. And now bisimilarity is itself a bisimilation. So we want to get to this fact that bisimilarity is the largest bisimilation. So first we have to prove that it's a bisimilation at all. And that's interestingly very simple to prove. We don't even need co-inductivity. Here, we don't need to conduct the co-inductive proof where we consider, so to say, arbitrarily many steps in our definition, but we can just use case distinction. This is what this thing is about, and this can be shown by this BLAST solver relatively easy with little help. We just say, basically, take the case distinction rule that follows from this co-inductive definition here and solve it automatically. So bisimilarity is a bisimulation. This is this bisim predicate that we had defined here. It progresses bilaterally to itself. And also bisimilarity is a simulation, right? Well, but that's very simple, because obviously any bisimulation is a simulation, because if it bilaterally progresses to itself, then also unilaterally, because the way bilateral progression is defined, it's unilateral progression, and then the one for the converses. And since bisimilarity is a bisimulation, this is the statement we have proven here, and trivially, bisimulation per definition is a simulation. Any bisimulation, then of course bisimilarity is a simulation. So this is just a lemma that could be useful later, but for what we want to prove here with that bisimilarity is the largest bisimulation, this was important. Bisimilarity is a bisimulation at all. Now we have to show that any bisimulation relation is smaller or equal, or is included in bisimilarity, and then we have it that it's the largest one. So, and that's the statement here, which is also not so complicated. In our old formalization of proof was much more complicated. Now it's pretty simple. Bisimulation in bisimilarity. For all k, the universal quantification is implicit. For all k, we have the following. If we assume that k is a bisimulation, then we can conclude that k is included in the bisimilarity relation. So if we go to the end of this block with our cursor, then we see the logical statement. So this doesn't use this outer syntax anymore, but it just says bisim k implies k is included in bisimilarity, which is also an important statement for conducting proofs, right? So if we want to show that certain things are bisimilar, we can pick a relation k and such that these two things are in this relation k, and then just show that k is included in bisimilarity. This is what I discussed before the diagrams. So if you can pick any relation k here and can show that transitions can be simulated by transitions such that we get into K again, then, and P is in relation with Q according to our K, then P is bisimilar to Q, because K as a bisimulation relation must be included in bisimilarity. And then, of course, we have the more convenient thing with the up-to methods. So, but why is this so? Well, the proof is also kind of almost automatic. We just have to do some technical stuff here to refer to P and Q that are related by K. So we have to go from this point-free to the point-full style. And then we just use our assumption and show that the fact that P and Q are related with K implies that they are bisimilar. And again, this goes by co-induction and sorting out some simple statements for that, and that's it. So, and now we have that bisimilarity is a bisimulation, and any bisimulation relation is in the bisimilarity relation. So obviously, bisimilarity is the greatest bisimulation relation, and this is what is state here. Our first theorem: bisimilarity is greatest bisimulation. Well, I call the theorem, I call these lemmas. That has nothing to do with logic. It's just for the convenience of the reader. Like in a mathematical paper, you distinguish between lemmas and theorems, but both are facts, both are things that you have proved. So the statement, that's the name of the theorem, right? And that's the logical statement. And this is just written like that, tilde, the bisimilarity, with a parenthesis. This is like this Haskell style, no, not operator sections, but that you treat the operator as on its own, not applied to certain arguments. This is the greatest K for which bisim K holds. So the standard library has already this structure where this K is a bound variable, which gives you the greatest K for which this property holds. Of course, you may wonder, what if there is no such K that this property holds? This is an expression. It must always have a result. What is the result then? It's not bottom like in Haskell, because bottom must not exist in a logical system like Isabelle. Well, the idea is then it's just undefined, right? Not undefined in the sense of Haskell that it's bottom, but it's unspecified, to be more precise, right? So if there would be no K for which bisim K is true, then this could have any result. And you could also not check what result it has, because it wouldn't be computable. It is not computable because it's just specified with logic, this greatest construct. And you couldn't get any information about what it is. So it would be just completely unspecified. But the specification says as soon as there is a K for which bisim holds, and there is a unique greatest one actually, then this term will give you this greatest one as a result. So it's also unspecified when you have the situation that there is no greatest one, that there are several maximal elements, for example. But here we have a particular greatest one. And now it's important to note, if you say this equals that, so a particular relation, the bisimilarity equals that, then this makes a bit more of a statement than you might expect. It does not just say something only that, okay, we know that there's a greatest one and this bisimilarity just happens to be the greatest one. But this statement in addition says, well, there is a greatest ones, right? So this statement says, let's say, three things. There's a K for which bisim K holds. There is a greatest such K, second. And the third thing is, this bisimilarity is the greatest such K, because if there would be no greatest such K, then this thing would be unspecified. And then we would have no opportunity to prove that it's just our bisimilarity relation that's equal to this. It could be, could not be, we don't know, because of this underspecification. So if we can prove that this is equal, then we have indirectly also the statement here proved that there really is such a greatest K in the first place. And we prove this by just using bisimilarity as bisimulation and each bisimulation is in the bisimilarity relation. This is what is using here says, by invoking an automated proof method with some statement from the standard library. And this basically tells us that we can make this step. So this is already a more higher level theorem or lemma that says, okay, the greatest x which fulfills the predicate P is our particular x, if and only if x does fulfill the predicate P, and for all y that fulfill the predicate, we know that y is smaller equal x. But these are precisely the things that we have here, right, for our particular case. This bisimilarity is bisimulation. This is this here in front. X fulfills predicate P. X is the bisimilarity now. P is the bisim predicate. And this other one here is essentially, no, exactly this bisimulation in bisimilarity. Right, so we can directly invoke this lemma here. I wonder why we need even the simplifier. I would think it should even a more simpler proof method that just applies a rule should suffice, but it doesn't for some reason. Don't ask me why, but maybe I can imagine why this is. Maybe because of some technicalities. Okay. Any questions until here? Everyone is silent.
Maybe you can explain the sim attribute, which is in a lemma below, sorry, above.
Which one? This one?
There's a lemma which the bisimilarity symmetry rule. Line 44. Line 44.
This one. Oh, sorry. This attribute. Okay. Yeah.
That's right.
Yeah. So this was a predicate, right? So it's the predicate. Okay, this argument.
Yes.
Symmetric relation, but this is something else. So this is our symmetry rule. So where we don't use this predicate is symmetric relation from the standard library, but where we spell this out explicitly. This implies that. So P bisimilar Q, then Q bisimilar P. And now we have this attribute here. So we had this with the simp and the if and only if, right? That we told certain reasoners to consider these facts automatically. Attributes can mean different things, but often these are some default facts to be used by certain reasoners. And it's like that with the sim as well. I'm just wondering where we need the sim or what reasoners use it. So there are also REFL and REFL, is there a REFL attribute? I think so. I'm not sure. But there's, for example, also a trans attribute. This is used, for example, if you do something like reasoning with equalities and inequalities where you have to chain certain steps, and this is automatically, then you need, under the hood, a transitivity rule needs to be invoked, and then the Isabelle machinery for this will just consider all the rules that were registered as transitivity rules with a trans attribute. I'm just wondering where you need the sim attribute. Honestly, I don't know right away. I think somewhere it's important, but I cannot really tell. But anyhow, it's a good idea to, if this has the structure of a symmetry rule, to mark it with the sim attribute. Same for transitivity rules with a trans attribute. And there are other such things. For example, monotonicity rules should be marked with a mono attribute, because monotonicity rules are in particular important in inductive and co-inductive definitions like this one, because there's this Tarski-Knuster theorem behind it, or maybe it's not Tarski-Knuster, because I think there's some confusion about what Tarski-Knuster really is. but this well-known theorem, which relies on these connectors from which you build these statements here after the if to be monotonic. And you can be quite flexible in Isabelle what you use. So you're not just confined to some logical compositions, but can also have your recursive occurrence of the relation you define under some arbitrary function, as long as this function is monotonic. But then you have to mark this function, then you have to prove a monotonicity rule for this function, mark it with this mono attribute, and these rules will be automatically considered. So the bottom line is that many things here are not hardwired. Many things work only if certain things are monotonic or transitive or symmetric or whatever. And we have a prover here. So this gives us the opportunity, or gives Isabelle the opportunity, to offer you also non-standard functions with certain properties to be used, for example, in these inductive and co-inductive definitions, as long as Isabelle can be sure that they have these required properties, but you have a prover and can prove these properties and pass these proof facts to Isabelle, and you make them to be being considered automatically by attaching these nice attributes to them. And that's the purpose of this sim. Next time, maybe we won't go through the details here. I don't know if this is so illuminating, because we will see the proving facilities of Isabelle in action with actually more interesting proofs, and then maybe we can have a closer look at these. So next time we will go to the definition of respectful functions. This, what I mentioned here already, that we can conclude from that something is a bisimulation up to f. We can conclude that it's included in the bisimilarity relation. If f is respectful, it's not necessary for it to be respectful, but it's sufficient. And so we will introduce the notion of respectfulness and see that how we can build more complicated respectful functions from simpler ones with this small algebra I have mentioned. And then we will get to the respectfulness, and then we will get to the actual up to methods. And here you have this thing what we already looked at, up simulation by simulation up to f, that's k progressives to f of k. And then finally, I will show you, maybe not next time, maybe next time, why these respectful functions can be used for this reasoning up to. And this will end the discussion of particularly simulation systems with some nice rules that allow us to use up to methods. Okay, then thank you very much for listening, and have a good time, and goodbye.